Welcome back to A320 Knowledge, your trusted source for Airbus expertise. Today, we'll be diving into a tutorial on A320 Green Operating Procedures. In today's tutorial, we'll explore the following: cost reduction strategies for A320 operations, efficient management of APU and air conditioning system, best practices and techniques for optimizing fuel consumption during all phases of flight. Each operator is responsible for deciding which costs and parameters they can optimize, considering aspects like maintenance, fuel consumption, and passenger comfort. It's important to understand that these guidelines are not universally applicable. Their effectiveness depends on factors such as geographical location, airport conditions, and local regulations. Therefore, flight crews must assess which procedures are most appropriate based on their specific operational context and the conditions of the day. As always, each operator has unique operational requirements, so it's essential to follow your specific FCTM guidance to ensure optimal performance and compliance. Prior to departure, the flight crew must accurately determine the necessary fuel quantity by evaluating various factors like weather conditions, performance factors, optimal flight levels, and average wind speed. It's crucial to note that carrying excess fuel can lead to increased fuel consumption, so precise calculations are essential. As a general guideline, the fuel penalty for carrying extra fuel is approximately 3% per hour of flight. For instance, on a 2-hour sector, up to 6% of the additional fuel could be consumed due to the increased weight of the aircraft. When selecting a takeoff configuration, fuel reduction should not be the primary focus. Instead, the flight crew should prioritize optimal takeoff performance based on various operational and environmental factors. The ideal takeoff configuration should maximize takeoff performance, considering factors such as takeoff weight. Where feasible, increase the flex temperature. Minimize takeoff speed by adopting a higher configuration for a specific flexible temperature. While using a higher setting for slats and flaps may lead to a slight increase in fuel consumption, it can ultimately result in cost savings when coupled with a higher flex temperature. Therefore, finding the right balance among these factors is crucial for achieving the best takeoff performance. When performance allows, using the highest flex temperature for takeoff is recommended. While this approach can increase fuel consumption compared to toga thrust due to a longer takeoff phase, it also reduces engine wear, contributing to lower overall operational costs. Flight crews should aim to delay the start of the auxiliary power unit as long as possible, opting to utilize ground electrical and pneumatic units when available. If conditions allow, set Pack 1 on and Pack 2 off for the first sector of the duty. For subsequent sectors, alternate the operation of the packs. During the external walk-around, flight crews should be vigilant for any defects that could lead to increased aerodynamic drag. Key issues to look out for include misaligned fuselage panels, flight control surfaces that aren't properly aligned, worn seals on the airframe, peeling paint, accumulated dirt on the aircraft. On the init page, verify that the cost index aligns with the computerized flight plan. The cost index represents the balance of time and fuel costs, and its purpose is not solely to minimize fuel consumption. Also, ensure that the tropopause value is correct to maintain the accuracy of flight management system predictions. When permissible, consider reducing the altitude for thrust reduction and acceleration altitudes, as regulations may allow a minimum of 400 feet. When selecting a runway for takeoff, prioritize performance and aim for the runway that minimizes taxi time and optimizes departure trajectory in order to reduce the flight time. If conditions permit, delay engine start until absolutely necessary. This strategy helps reduce time with engines running pre-takeoff. However, ensure proper engine warm-up to maintain performance and prevent wear. If the APU is needed during or after taxi, such as when takeoff performance requires APU bleed, the flight crew can turn the APU bleed on to help lower fuel consumption. Activating the APU bleed opens the crossbleed valve and automatically closes the engine bleed, meaning that bleed air is sourced from the APU instead of the engines, which reduces overall fuel use. However, it's important to note that using APU bleed may result in the ingestion of exhaust gases into the air conditioning system. During taxi, idle thrust is generally sufficient for a light aircraft. Excessive thrust not only burns more fuel, but can also lead to increased brake wear. Before takeoff, it's advisable to turn both packs off to conserve energy and enhance engine performance. Disabling the air conditioning packs helps free up additional engine thrust, which is particularly beneficial during the critical phases of takeoff and initial climb. Once airborne, the flight crew should use managed speed during the climb unless restricted by ATC. This practice allows the aircraft to fly at the optimum econ speed, which is vital for balancing fuel efficiency with time management during the climb. Additionally, it's important to adhere to speed limitations below 10,000 feet. The flight management system typically enforces the 250 knot speed restriction in this altitude range. Complying with this guideline not only ensures regulatory adherence, but also enhances overall flight safety and efficiency. During cruise, the optimum flight level increases as the aircraft's weight decreases. It's essential for the flight crew to monitor the optimum flight level continuously and adjust their altitude to achieve the best aircraft performance and fuel efficiency. The flight crew should regularly input accurate and current wind data into the flight management system to enhance fuel predictions and determine the optimum flight level. It's important to update wind information whenever there is a change greater than 30 degrees in direction or 30 knots in speed. The flight crew should utilize managed speed mode to maintain econ speed, optimizing their speed in line with the cost index and current flight conditions. It's crucial that the flight crew does not alter the cost index while in flight to ensure consistent performance and efficiency. When conditions allow, the flight crew should request to land on the runway that minimizes both approach and taxi times. To reduce fuel costs and prevent brake oxidation, the optimal configuration during landing is to use config 3, reverse idle and auto brake low. When landing performance allows, selecting config 3 not only shortens the approach time, but also contributes to lower fuel consumption. If a shorter landing distance is required, the flight crew can utilize the deceleration devices in the following order: flaps full, reverse max, then auto brake medium. However, the flight crew should avoid using auto brake medium in conjunction with config 3 and reverse idle, as this combination can significantly raise brake temperatures, leading to severe brake oxidation. When conditions and ATC allow, a decelerated approach can effectively reduce fuel consumption. If a decelerated approach is not feasible, then the flight crew should aim for an early stabilized approach. In a holding pattern, maintaining a clean configuration is the most effective option, and the flight crew should aim to maintain green dot speed. This speed is crucial for optimizing the lift-to-drag ratio and conserves the most fuel. If the holding pattern has a speed limitation, the flight crew may consider selecting config 1 for the hold. After landing, the flight crew should postpone the start of the APU for as long as possible to conserve fuel. If the only ground pneumatic unit available at the gate is in use, the flight crew can keep the APU bleed off during transit, further minimizing fuel consumption. During two-engine taxi operations, both packs should remain in use to ensure passenger comfort and system efficiency. When conducting single-engine taxi-in procedures, the aircraft will automatically revert to single-pack operations, with Pack 1 receiving supply from Engine 1. Once the aircraft is on stand, and if environmental conditions permit, the flight crew should follow the guidelines outlined in their preliminary cockpit preparation SOPs for operating on a single pack. One-engine taxi procedures typically involve shutting down Engine 2 and activating the yellow electric pump approximately 2.5 to 3 minutes after the thrust reversers have been stowed. Always consult your company's procedures to ensure compliance with the established guidelines. Thanks for tuning in to this tutorial on A320 Green Operating Procedures.